limiting reactant in moles per unit time that is fed into the reactor, not into the overall process. Then in one pass, in one residence time tau, which depends on the volume of the reactor and the flow rate, and divided through by that, one divided by the other is a measure of the residence time. So you will have some conversion. So you measure the limiting reactant coming out of the vessel, the reactor. That's your second term in the numerator. And then you normalize it by how many moles per unit time of the limiting reactant is fed into the reactor. And that is a single pass conversion. So the single pass conversion is always less than or equal to the overall conversion. That is the way, basically based on this definition. Okay. So suppose I just take an ideal example. Let us say you have a reaction A going to B, and let us say you are feeding into the fresh feed 75 moles per minute of A. Now the recycled stream joins it, and that contains 25 moles per minute of A. So the total stream is 100 moles per minute of the limiting reactant A. This goes to the reactor, and of course in a single pass you won't get complete conversion. So let us say 25 moles per minute of A remains unreacted. So you get 75 moles per minute of B, because it's A, just one A going to one B. So 1 mole to 1 mole from the stoichiometry. So you have from the reactor input 100 moles A per minute, 75 moles of B per minute, and 25 moles A per minute. Now let us say this product separation is ideal. So how many moles B per minute will go into the product? The complete thing, all of B. So that is the final output. And as I said, 25 of the unreacted A per minute you are recycling back into the fresh feed. So now for this problem, find the overall conversion. Based on this definition above. You remember in the question I gave you, we had defined the overall conversion in the dehydrogenation question. So I think we jumped the gun. We should first have done the definition and then gone to the question. It's fine. It'll be a bit of a repetition perhaps for some of you.
Sir, are you talking about the last question you gave in the class?
Yeah, but this is a different one. Here I've just taken a fictitious problem based on which what I gave last time is of course a better example. But first we should, for the question I just described to you, find the overall conversion.
Sir, but your slide is stuck on this 43 one only, sir.
Yeah, there is no slide for this, no, because this is not part of the. I just gave you an example. No, I don't think there is any slide for this. Let us see. Maybe yes. Okay, all right. You must not confuse the two conversions in any question. If it's given overall, then apply the dehydrogenation, apply the correct formula.
Sir, overall conversion for A should be 100%.
Yes, because nothing is going in the output. 25 moles per minute is coming in, and the numerator and denominator are the same. So of course you are getting 100%. Now what about the single pass? Why is the overall conversion 100%? Because you have assumed that the second vessel ideally separates A from B. This is never true, by the way. So what you could do is you could completely separate 75 moles B per minute and 25 moles A per minute, which was what was fed into the separator. I don't think there is any known process like that, ideal. That is why you are getting an overall conversion of 100. If that efficiency of the separator was not complete, and which is what we have in the question that I left you with last time, and that's what we need to look at, then you are never going to get 100% overall conversion. Whatever A is not there, is you are immediately recycling all. No. So the overall conversion would be less than equal to 100%, and single pass will always be lower than the overall conversion. These are the two, and we can actually prove that.
So single pass would be 75%.
Right, because 100 moles per A minute is coming in, only 25 moles per A per minute is going out of the reactor, and you have normalized it by the reactor input, what is coming into the input of the A, which is 100, so it's 75%. So now you can apply this to the question of dehydrogenation that we just went towards, which some had started. So this was that question. So see if you can work out. And the difference here is the separator is not working at 100% efficiency. So some C3H6 will also to the recycle stream. So that if you take 100 moles, some few moles will be in the recycle stream. And similarly, there will be some Q product moles of, Q in the product stream, there will be moles of C3H8. So you'll have all three in the product stream. and you will have the limiting reactant and the product in the recycle stream. So you have to separately give symbols for them.
So as far as the minors are concerned, so
Yeah,
till when?
we have it on 8th. Is that correct?
Yes, we are like minors are starting from 8. I'm not
So when
sure.
do we have ours?
So 8, sir.
So basically, since it's my first online thing, how is that exam generally administered? You would have done this last semester, right?
So like they used two methods last semester. Like one was Moodle based, wherein they gave like MCQ based papers, like
Okay.
basically objective papers, and they conducted it via Moodle. And the second was they gave like a subjective paper and asked us to scan our answer sheets and upload them on a platform.
Okay, but in the objective type of thing, but you what about the problem statement? How is that uploaded or made available to you?
So like they can like upload either an image or they can type it out.
Oh, okay, okay, all right. Right, you were asking something. Somebody was asking something.
So I was asking the syllabus or the last slide till where the a minor one would come.
I mean, basically, I mean, energy balance we have to start next week. Oh, of course, energy balance we will not make much progress, so there's no point in asking that. And also, I just want that next week you worry about forming a group of 5 or 6 and come up with that group, because we definitely want that happening. So that's something that you can discuss among yourself, and next Monday you can do that. By tomorrow we will finish this course. In Wednesday I can start you the energy balance, just introduce you, and then we have to go through the same loop like we did for mass balance. We have to do that for energy balance, but I think we will go a little fast. Well, by end of November we want to finish the course, which includes 2 extra classes of 3 hours each, or 1 extra class of 6 hours on Sunday, right? So that after mid-sem break, since I'm out for 2 weeks, so that's also that would be the biological portion. So we have to finish the energy balance by just before, say, November 26th or 25th, something like that. And then one Sunday we will together do the bio part. So that will be the whole thing. Then you can easily, with the group that you have made next week, you can worry about choosing any flow sheet, and you have all the 3 things done: mass, energy, combined mass energy in the bio part. energy balance we can't cover in 2 lectures. I mean, we will start on Wednesday. So maybe you should just make the group Monday. Tomorrow we will finish this part, which is what will be for mine. So if you take 100 moles, 100 moles per unit time go of C3H8 in the fresh feed, what you have to now find out is, you don't know pretty much anything about the recycle stream. Nothing's given to you. I mean, nothing means you have given some information, but you'll have to choose symbols for that variable, for those variables. Then once you choose those variables, so you have some Q recycle for the total recycle stream, and that plus 100 will be the input feed to the reactor.
So also like since we've given like 95% overall conversion, that means like since 100 mole is entering, that means like 5 mole should be leaving
That's right. That is
the
right.
output.
That is right. The output will be 5 moles.
Yeah, and it's given 5 is 0.555% of what leaves the reactor.
That's right.
So we can find the remaining, like what amount leaves the reactor.
Right, but that still will not give you the recycle ratio or the single pass conversion. Definitely you will have to do that, but you'll have to do something more too. But anyway, let's go step by step. So you do not know the moles of C3H6, C3H8 and out of the reactor. So you have to give variables for that. Similarly, the product will have all the 3 after the separator. And since the limiting reactant question doesn't arise here, it's C3H8, you will have only C3H8 and C3H6 being recycled. Because it clearly says that the second stream just contains unreacted propane and propylene. So those two also you have to label. So that's what your diagram will contain. Something like so generally I don't use M dots and N dots and all generally. So like what I meant and what he calls N1, N2, I meant as Q recycle C3H8 and Q recycle C3H6 plus 100. So 100 is the basis. Then I told you that output of the reactor, all the 3 streams are unknown. So he has called them N3, N4, N5. I generally call them some P1, P2, P3, whatever. Then separator has what I call Q recycle 1, Q recycle 2. He has called them N9 and 10. So Q recycle 1 was moles of C3H8, other one was C3H6. So he has it's fine. He has called them N9 and 10. Product contains all the 3. So those are labeled. So that is Q without, for me, Q without the recycle stream, Q1, Q2, Q3. But if you want, you can call it N6, N7, N8 as he has done. So in this, you have to find, because 100 is coming in, what you have to find is in his notation N1 plus N2 upon 100. For the recycle ratio.
So for the cycle ratio, I guess N9 plus N10 upon 100 would be the recycle ratio, no? Right?
Yeah,
N9
N9 plus
plus
N10, N9 plus N9 plus N10 upon 100.
right. So N9 can be found out by this product minus reactor stream, like N6 minus N3. So
And so N6 we know like it's 5 plus 95% conversion.
Well, I suggest you first use the overall conversion like somebody suggested, and you said that it's 95. उससे आप शुरू करिए. Product में कितना C3H8 है, you will know. So first do use that, please. You know the definition of overall conversion, we just did it. So that has only one variable, the second term in the numerator. Find that term. So that will give you N5, right, in his symbol, or what is it, N6 rather. That will give you N6 in this notation. Hundred minus N6 upon 100 is 0.95.
Yes, so N6 is 5.
So that is the first one stream in the product. Now you can do the overall balances on C3H8 and C3H6.
So, but before that, like we know like N6 is 0.55% of N3.
Right.
So we can find N3 using that.
All right, all right. How much is that?
So that comes out to be 900.
Okay. So that means you also have N3 now. Label it. But you cannot do the same on the recycle because you don't know both of them yet.
So also this.
But in the recycle stream, since like we know that N9 would be N3 minus N6.
Okay.
So like we can find out, because we found N3, we found N6, so we can find N9 using that as well.
All right. What does that work out to be? How much?
So 900 minus 5, that will be 895.
Okay,
Yes.
very good.
And using that, we can find N1.
All right. Okay.
And then N1 minus N3 will be N4 minus N2, because like the net conversion in the reactor should be same.
All right. I mean, okay. I'm all right till. So at least put that value of recycle stream N9 whatever you get 895. इसको डालो तो सही आप. That means if you do the overall balance, you are going to get N6, N7, N8 also you will get. So N8 will be also 95 moles.
Yes, sir. So we can do that by the reaction itself. Like 1 mole of C3H6 would be formed for the 1 mole of C3H8.
Right.
Yeah.
So from propylene balance and H2 balance, you have both of those as
Yes.
95. So you know N6, N7, N8. You have just found out N. Now you just have to find N10, which you can do because you have one more. You have been told what the composition is of that stream. 5% of the propylene in the product stream is recycled, no? So that also should use.
Yes, sir. So that would be 0.05 of this. Yeah, of this 95.
5, correct. So 0.5. I mean 5% of 95 will be
4.75 mole.
N10. Right. So that will be 4.75 moles.
So the recycle ratio would be 9. 9.
Correct, because
895 plus 4.75.
895 plus 5. So 900 upon 100.
So how did you like take 9 N7 to be 95? I didn't understand that. Like N8 will be 95, but why N7?
Because 95 moles of the C3H8 reacted and 1:1 was the stoichiometry.
Yeah, so but like 95 moles reacted, so that will be N2 minus N4 minus N2, right? 95, because the net increment of C3H6 in the reactor is N4 minus N2, and that net increment should be 95.
No, I'm just doing an overall balance. Overall conversion is given to you. 100 was going in.
Okay, yeah, correct. Yeah.
Correct. So
Yeah.
from that I get 95. So the recycle thing will be 895 plus 4.75 upon 100. Almost 9. 9 moles of total recycle per mole of fresh feed. Then now you can even find the single pass conversion.
Yes, sir. So single pass would be 100 plus N9, this, and then
That was
minus
895. So 100 plus
N3.
So that's
895
995.
minus 900.
Yeah. 95 by 995.
95 by 100 plus 895. Yes. So that's
Then
getting
9 plus
10%.
995 upon 9.
9.5%.
Yeah, now you know all the streams, so you can calculate everything. Exactly. So basically input was 100 plus 895 moles of C3H8. So that is 995 minus the output was what you have called N3. So that was 900 because you just calculated that from the 0.0555, right, fraction. So that gave you 900, you told me. So that's 900. So 100 plus 895 is 995 minus 900. So 95 divided by 100 plus
895. That's
what fit into the
yeah.
thing, which is 895, right?
This is 9.5%.
Not 8, a little less than 10%.
Yeah.
9.5%.
Yeah, 9.5%.
Yeah. So everybody can revise that. So now, so these are the types of reaction questions, you know. I mean, you can make many combinations of them. Maybe what have I missed? I'm just, um, yeah. I mean, there are all these incomplete combustion problems. So you can just take one of them, and maybe next time we can worry about them. Uh, let's take this down. There's just so many variants of it. So here it's exactly like the earlier problem, but that time we had complete combustion of methane. Now you can have incomplete combustion of methane. So why don't you take a look at this, and next time we can discuss it. And if there's anything else, we can. So then I will just just decide what to do in energy balance, how much time I have, because we can go through exactly the same thing, but we don't have full month time. A little less because we have to do the bio part also. Since I'm not available for 2 weeks after your midsem break. So let me see how best to do it. Monday, meanwhile, if you can make the groups, that would be very good. But for tomorrow, we will complete this portion for your minor. Okay, so I don't know. I tried to communicate as simply as possible. I'm not sure. And later on, we sort of jumped the gun. I also got a little bit bored and missed all the definitions. But I think it's all very natural. You are pretty good at all these type of calculations. The only thing is you have to do it systematically in a time available. Last time I sort of gave a little difficult minor in the sense that I took my own humidity, I took it out from my humidification background and gave a little complex problem. It could not be done in 1 hour. So this time I'll give you something which you can definitely complete within 1 hour. Except for one person, nobody completed the paper, so I didn't know it would take that much time. So you never know, I mean, so that was the first time I was taking this class. So this time I'll give you something which everybody can solve in 1 hour.
So I had a doubt. In this question, you have written carry out the degree of freedom analysis of the process.
Yeah, we haven't actually done that. So degree of freedom is something that we have to do. I have missed it out. What you can say, degree of freedom is number of independent equations, rather number of variables in the problem minus number of independent equations. That is the degree of freedom. That is how we define it.
Okay.
So identify the number of variables, identify the number of pieces of information that you have. I only did it for a non-reactive system. I said it's equal to the number of components, but we didn't do this in general actually. So I'm not going to ask you that. There are a lot of mathematical things that one can do in such things. It's even today there can be research questions on graph theory based things you can do for reactions, multiple reactions, and so on, and prove many nice results. If somebody is interested in mathematical analysis of networks, even today I find chemical engineering science and other journals carrying mathematical and graph theory based network based proofs, mathematical proofs of these. Anyway, but that's something I just left you with that question, but we never completed it. So leave that part. Okay, so to summarize, I think we are more or less towards the end. We started from very simple non-reactive systems and then went to little more complicated non-reactive problems. And then we added one reaction, multiple reactions. Then we added recycle two reactions. And I think that's really what we wanted to cover. So if you have any queries or anything, we'll complete it tomorrow, and that's your course. Is that all right?
Yes, sir.
So, there's a question. So, in this question, this N2 would be inert. So, I guess this the molar composition in the final molar composition N2 would remain 72.8% only, no?
Right, but that's right. There's no reaction with N2.
Okay.
Not in the molar composition, right? Because
Yeah,
the
not in
number
the
of
molar,
moles
of course, of course.
the net number of moles of N2 will be constant.
Of course, exactly. We'll worry about it. Yeah, you're right. You have it right. Yeah, that's correct. Very well then. We will complete this tomorrow, and thank you for your attention.